Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Zaimi bin Muhammad Zain. I am from Group 10. So, this is our members. So, our topic is circuit and graph coloring. For the first table of content is Euler cycle. Second is Hamilton circuit. Third is graph coloring. Fourth is coloring theorem. And lastly is application of Euler, Hamilton circuit and graph coloring. First subtopic is Euler cycle. So the difference of Euler path and Euler circuit. First of all is definition. What is Euler path? Euler path is path that pass the through each edge of a graph exactly one time. Next is Euler circuit. Circuit that pass through each edge of graph exactly one time. So the difference between an Euler path and Euler circuit is that Euler circuit must start and end at the same vertex. We can see through example. For the first graph, which is the Euler path, and second is Euler circuit. So you can see two different graph from both of graph. You can see from Euler circuit. Euler circuit has another point which is F. So D point is connected to F and E is connected to F. So you can see two different graph. For the answer for Euler path is DEBC ABDCE, and for the graph Euler circuit is DEB CABD CEFD. Next is a degree of vertex. What is degree of vertex? The degree of vertex is the number of edge of the vertex. So I give you another example. A is connected to D. So the vertex of A is 1. Next is B. B is connected to D. So the vertex of degree for B is 1. And C, you can see same as AB. So the vertex of degree is 1. But you can see for D, D is connected to A, B, C, and E. So there are 4 degree of vertex. You get 1, 2, 3, and 4. So the answer is 4. Next is E. You can see E is connected to D, F, H, G. So there are 4 degree of vertex. And F same as ABC, just 1. So for H is connected to E, G, and I. So there are 3 degree of vertex. So I is connected to H, I connected to J, so there are 2. J connected to I, and G, so there are 2. For the next example, we can see through a map. So a question is it possible to travel among the states and cross each common state border exactly one time? Second is, is it possible, can he or she start and end in the same state? So, to make an easy for the answers, we create a multigraph. You can see this is exactly through a map. So the answer is Euler path. Use each edge exactly one time. There are 2 odd vertices. The graph has at least 1 Euler path but no Euler circuits. And yes, is it possible to travel among this state and cross each common border exactly one time? So the answer for second is there is not an Euler circuit. So the researcher cannot start and end in the same state.
My name is Shen. My metric number is 207273. So today I'm going to share about Hamilton circuit, which is proposed by William Rowan Hamilton. So Hamilton circuit is actually a simple circuit in graph G that passes through every vertex exactly once and finally will back to the original point, meaning to say the starting point and the ending point of the graph is at the same vertex. So it's like this. For example, when we start from A, so I can go to C and go to B and go to D and back to A. So this is one of the Hamilton circuit in Hamilton graph. There are two theorems that can be used to determine Hamilton circuits. So the first one is direct theorem, and the second one is O's theorem. So the direct theorem is happens if G is simple graph with n vertices, vertices in number of n, with the number of vertices is greater or equals to 3, such that the degree of every vertex in G is at least the number of vertices divided by 2. So there are 4 vertices, A, B, C, D. So there are 4 vertices. So meaning to say the number of vertices is greater than 3. So 4 divided by 2 will becomes 2. So the degree of every vertex is 1, 2, 3. So every vertex will have 3 degrees. So 3 is greater than 2. That is Hamilton circuits inside the graph, meaning to say the graph is Hamilton graph. The second theory is Or's theorem. Or's theorems happen if G is simple graph with n vertices with n greater than 3, like the direct theorem here, like the part here. That is another requirement for Or's theorem is the degree of U and degree of V. The U and the V must be the non-adjacent vertices. The summation of degree of U and degree of V must greater or equals to the number of vertices. So, for example, the vertex A, so the non-adjacent vertex for A is C. So AC. We can find 3 pairs of non-adjacent vertices, which is AC, BD, and BE. So the sum of the degree of the vertex are AC. A here we have 3 degree, and C we have 3 degrees. So the sum of AC is 6 degrees. Yeah, and same goes to BE. So we got 6 degrees and 5 degrees and 5 degrees. So there are 5 vertices. So the number of vertices is greater than 3, which and this fulfill the first requirement. And the sum of degrees of every non-adjacent vertices are greater or equals to 5. 6, 5, 5. 6 and 5 are equals to greater and equals to 5. So the graph has sufficient condition to be Hamiltonian. However, there are weakness for the two theorems. So the weakness is the theorems is just a sufficient condition for a graph to be Hamiltonian. Meaning to say, the graph without following the two theorems doesn't mean that the graph is not Hamiltonian. So this can be proved by using the two theorems also. First, I prove using the direct theorem. So there are 5 vertices A, B, C, D, E. So the n should be 5. So 5 is bigger than 3. So this obey to the first requirement for the direct rules, direct theorems. So 5 divided by 2, we will get 2.5. So the degree of all vertices, so A, we have 2 degree, 2 degree, 2 degree, 2 degree. So meaning to say A, B, C, D, E, D have 2 degrees. So 2 is smaller than 2.5. So if according to the theorem, this is not Hamiltonian, but however, I'll show you how to construct a Hamiltonian circuits here. So for example, we go from A to B to C to D to E and back to A. So this is actually a Hamiltonian circuit. So this can prove that the theorem are just sufficient condition. So the graph without following the two theorems doesn't mean that the graph is not Hamiltonian. And I prove using the second theory, which is the Or's theorem. So there are 5 vertices also, A, B, C, D, E, and the number of vertices is greater than 3. And the pair of non-adjacent vertices A, C, B, D, C, E, D, A, and E, B. So the number of the degree of at every vertex is 2. So 2 plus 2 equals 4, 4, 4, 4, 4. So the sum of degree of every non-adjacent pairs are lower than 5. So which means if according to the theorem, this is not Hamiltonian. But like what I said just now, although some of the graph does not follow the theorem, but there might be Hamiltonian also. So for example, A go to B, go to C, D, E, and back to A. So this is actually a Hamiltonian circuit.
Assalamualaikum and hello Madam Anita. My name is Muhamad Hazim bin Shaharudin. My matrix number is 206209. So I will be presenting the subtopic graph coloring. The definition of graph coloring is a coloring of a simple graph is the assignment of a color to each vertex of the graph so that no two adjacent vertices are the same color. From this definition, we could say that two vertices that is connected to each other by a line or an edge, both vertices cannot be the same color. Here is the example. If there is only one vertex, that means there is no edges or line connected to it, then there will only be one color. If there are two vertices that connected to each other, then there will be two colors assigned to the vertices. If there are three vertices connected to each other, then it goes with three colors. There are four terms commonly used in this subtopic. Firstly is chromatic number. Chromatic number is the least number of colors needed to color a graph. This definition is already straightforward, where it means that the least amount of colors used to color a graph is called chromatic number. It is denoted as Xg, where G is the graph. For the graphical parameters, the least chromatic number can be is 1 and the highest is n, where n is the number of vertices. To be clear out, here is the example. In this graph, there are 6 vertices. It can be assigned with 2 colors, 3 colors, and 6 colors. According to the definition of chromatic number, so the 2 colors would be the chromatic number. The next term is independence number. Independence number is the maximum size of an independent set. It is denoted as alpha G, and the graphical parameters is similar to the chromatic number, which is the least is 1 and the highest is number of vertices. It is hard to elaborate just by looking at the definition, so I will be explaining through the example. So here is given a graph. First of all, we will be looking for the independent set. Independent set is a set of a vertex or vertices that is not connected to a certain vertex. For example, vertex A and C is not connected to each other. Therefore, they can form an independent set. So from this graph, we can have 5 independent sets. The set is AC, CE, AE, BE, and AD. All of the vertex is not connected to each pair. However, independent set is not only limited to 2 vertices. If we can add another vertex to the set, then that is what we will be looking for. So from this graph, we can have an independent set consists of vertices ACE. But be careful, not all of the vertex can be included to the set. For example, the set ABE and the set CDE, both are not an independent set. It is because although the vertex A and E is not connected, and the vertex B and E is not connected, just because the vertex A and B is connected, therefore that makes it not an independent set. Same goes to the set CDE. Although the vertex C and E is not connected, but the vertex C and D is connected, and the vertex D and E is connected. Therefore, it is also not an independent set. Looking back to the set ACE, let's assign it as a set S. Then to find the independence number, we will be taking the cardinality of the set. Therefore, that makes the independence number of the graph is 3. The third term is clique number. The clique number of a graph G is the largest n such that Kn is a subgraph of G. This definition tells that the clique number is the largest number of vertices of a complete graph of a subgraph. It is quite difficult to understand, so I will be showing an example. Here is an example graph. Firstly, we need to find the subgraph. Subgraph is some vertices that are connected and they are part of the graph. There are a lot of subgraphs in this graph. For example, this is a subgraph consists of vertices C, D, E, and F. Then we will need to find clique. Clique is also a subgraph, but it is a complete graph. In this graph, there are a few clique. For example, this is a subgraph of B, C, and F, and this is a subgraph consists of vertices A, B, and F. For the next step, we need to see if there is any bigger clique or whether the clique can be extended bigger. So in this example, there is one bigger clique. That is, a subgraph consists of vertices A, B, C, and F. Then we need to find if there is any bigger clique, or maybe if it possible to be extended. If there is none, then it is called maximal clique, where it means that it cannot be extended anymore. Then in order to find the clique number is the amount of vertices of the maximal clique. Therefore, for this graph, it is the clique number is 4. The last term is chromatic index. Chromatic index is the least number of colors needed to color the edges of a graph. It is denoted as X'(G). So this time we do not color the vertices, instead we color the edges. But the concept is still similar, where we assign colors if the edges are adjacent. In other words, the edges are incident on the same vertex. So for example, we have a graph of 6 vertices, can be assigned with 2 colors, 3 colors, and 6 colors. So since the chromatic index is the least number of colors, so the graph with 2 colors is the chromatic index.
For the next subtopic is coloring theorem. The 4-color theorem. For any planar graph, the chromatic number of the graph is less than or equal to 4. Thus, any map can be properly colored with 4 or fewer colors. Brooks' theorem. The chromatic number of graph is at most the maximum vertex degree. It gives the meaning that every graph actually satisfies Xg less than delta G, unless the graph is a complete graph or an odd cycle, in which case X parenthesis G equal delta parenthesis G plus 1 colors are required. Next is Weissing theorems. Weissing's theorem states that a graph can be each colored in either delta or delta plus 1 colors, where delta is the maximum vertex degree of the graph. In other words, for any graph G, the chromatic index Xg is either delta G or delta G plus 1. This partition graph into 2 classes, with the one require delta colors known as class 1 and the one require delta plus 1 colors known as class 2 graph. Theorem: if H is a subgraph of G, SH less than SG. Any coloring of graph G provides a proper coloring of subgraph H simply by assigning the same colors to vertices of H that they have in G. This means that subgraph H can be colored with XG colors or fewer. Theorems: the chromatic number of graph G is at least the clique number of G. The graph which its chromatic numbers equals to its clique number is called as perfect. Hence, if any graph is already known as perfect, the chromatic number can easily be found by looking for the largest clique. Next is application of Euler-Hamilton circuit and graph coloring. There are a lot of application of Euler, but I give you just one, which is DNA fragment assembly. So DNA is a deoxyribonucleic acid. It's found in every living organism and is a storage medium for genetic information. A DNA strand is composed of pairs which are denoted by A is adenine, C is cytosine, G is guanine, and T is thymine. The familiar DNA double helix arises by the bondage of 2 separate strands with the Watson-Crick complementary. A and T are complementary, C and G are complementary also, leading to the formation of such a double strand. DNA sequencing and fragment assembly is the DNA problem of reconstructing full strand of DNA based on the pieces of data recorded. It is of interest to note that ideas from graph theory, especially Eulerian circuit have been used in a recently proposed approach to the problem of DNA fragment assembly.
So the application of Hamiltonian circuits is traveling salesperson problem. It can be also known as traveling salesman problems. It's a method to find the shortest and the most efficient route. This method is widely used in logistics and transportation. For example, a company J and T want to deliver an object from a city to another city. So, for example, if you start from the first point, and then finally it will back to the first point also. The knowledge of Hamilton circuits can be used here. So, for example, it can be go to 2, 4, 3, 6, and 5, and 7, and back to the original point. This can help the logistic company to make the delivery journey to be the lowest, to save the cost and save time and even save the petrol fee. So that's all from me. Thank you.
Application of graph coloring. There are a lot of applications of graph coloring in real life. One of them is guarding an art gallery. The situation is, in these modern days, the art gallery can be secured using CCTV cameras. The cameras have to be positioned precisely so that every angle in the gallery can be captured. So the problem is, we need to use the least number of cameras as possible in order to save the cost of the camera or the electricity, and it is also easier for the security to watch all of the TV screens at a time. We begin with our first step. We must have the floor plan of the gallery. The second step, draw a simple planar graph, and the third step, draw a possible triangle shape by connecting two corners where each triangle covers a certain area in the gallery. Lastly, we put vertices on all of the corners in the graph, and since the graph is full of triangle shapes, therefore according to chromatic number, we would need to use 3 colors. As a result, we can choose either to place the camera to the black vertices or green vertices.